Let's get started by reviewing some of the important terms and basic properties that we've covered. Pause the video and see if you can name all of these terms. I, we know, is the moment of inertia of the area. J is the polar moment. C is the distance to the outermost fiber. And A is the neutral axis, which we find by doing a first moment analysis. Q is the first moment beyond the cut, which is used for horizontal shear. Y is just our vertical distance from the neutral axis generally. LE is the effective length used in columns for buckling. And all of these are geometric values that we would have to compute for different types of stress and strain that we might be analyzing. J is used quite often for shear stress under torque. I turns up in quite a few of our equations for bending. Q turns up for horizontal shear, length effective for buckling in columns. And then we have the material properties. E is Young's modulus of elasticity, which we know pops up when we're doing stress-strain relationships. G is the shear modulus of elasticity, which when we're under torsion will generate a shear stress, and that'll be a shear strain. That's our Poisson's ratio, which relates one axis to the other. Here's our normal stress and our shear stress terms. And then we have a bunch of different loads that we could apply to this thing. P is usually used to be an axial, compressive, or tensile load. T is a torque for us, applied to the end of a shaft. V would be a vertical shear, internal to a beam. M is your moment, also internal, usually from V and M diagrams. And I guess we could also add W as a function of X, which would be a distributed load. And certainly you could also have concentrated load. And if you think about it all semester long, bit by bit, we've introduced all of these types of terms and worked with them separately. But now we want to look at what happens to a system when they're all being combined and working together. And the short answer is we use superposition, which tells us that we can take all of the individual loads and address them one at a time and then add up the pieces and parts to get the total load, stress, and strain acting on a member. Here's a partial list of some of the key types of stress that we analyzed throughout this course. Pause the video and see if you can write down the equation associated with each type. The axial normal stress equation is simply force per unit area, and that generates a tension or a compression effect inside of a member. Our bending stress equation is written as negative mc on I, although we often ignore the negative and just do the analysis ourselves. If we're not at the outermost fiber C, the equation's also valid as my on I. For example, if we want to know what the stress was here on the bottom half of that flange, we would use the distance from the neutral axis to that flange in that equation, and we can find that. And that'd be true for any other point inside of this I-beam cross-section as well. If we had a member that was undergoing a torsion, we could use our tau is equal to Tc on J, where again, C is the distance to the outermost fiber. And if we were looking for some shear stress that's on the inside of the tube rather than the outside of the tube, let's say, we could use R instead of C. And for horizontal shearing stress, tau would be equal to VQ on IT, where Q is the first moment of the area beyond the cut, and T is the actual thickness of the cut that's required to free up that area. And recall also the shear force flow equation that went with that, which is equal to VQ on I, and that we use to determine bolt spacing, things like that. So there's a good review of some of the key terms, some of the key equations that we looked at for calculating different types of stress. And all of these could be of concern when we're analyzing a loaded member. Let's take a look at the effect of different types of loads at different locations within a beam. So here we have three possible elements. A and B are at the outermost fibers, and C is at the center on the neutral axis. And if we have a compressive load P, we know that that generates a normal stress of P on A, and that would act uniformly on all three of these. So the location in that case would not matter. The stress would simply be P on A, and they'd all be in compression. So that's one of our easier types of loads. If we take a look at a bending moment applied to a beam, recall that the upper regions would be in compression, the lower regions would be in tension, and at C, the bending stress would be 0. We don't generate any stress on the neutral axis, and recall that these linearly increase as we move away from the neutral axis. So here the location in the beam is important in terms of calculating the maximum stress due to a bending moment. If we take a look at a torque that's being applied to a shaft or a column, we can see that it's going to uniformly shear all these elements along the outer edge. And if we look at the cross section, we could picture each of these elements, A, B, C, and even D maybe on the other side. As the torque is applied here, each of these would experience on the top of their face a little shear, and it would be the same value since they're all the same R distance away from there. So when we look at it over here, we want to envision that this is on the side face of it. And these little elements, if we're looking at them, would deform like this. So when we apply a torque, T, it helps to imagine the direction that the small elements would deform, and then we can get a sense of what the tau is doing on that element right there. If we look at a shearing stress being applied to a beam, we can see that there'd be a shear force here generated at the center, tau, and it will be 0 at the outer fibers. And that occurs because tau is a direct function of Q, where Q is defined as the first moment of the area beyond the cut. So if we have a cut up here, we're talking about this region right there, and our Y bar would be the Y bar distance to its center. And we can see as the cut moves further up away from the neutral axis, the remaining area is going to get smaller and smaller to the point where Q at the top goes to 0, and Q above the neutral axis would be a max. So we expect to see tau being a max on the neutral axis and being 0 at the outermost fibers, which interestingly is exactly opposite of the bending stresses. Will be a max at the outermost fibers, and they'll be 0 on the neutral axis. And that's handy to keep in mind. We run into that scenario quite a bit with these types of beams. And then it's a really fun day when we have potentially all of them acting at once, and we have to carefully go through and address them one at a time. And here's where superposition plays an important role, because superposition allows us to address this one load at a time, one form of stress at a time, and then add all of those individual components together to get the final state of stress inside of our beam. Here we have a pole that's going to support a large highway sign. The weight of the sign is 2 kips acting down here. There's a force from the wind blowing on it. And we're also given that the pole itself is going to have some weight acting down. And we're asked to find the overall safety factor for this steel column. It's a 6-inch diameter, 1/4-inch wall pipe. Let's start by looking up the values for steel. Referring to our tables or the manufacturers, we find these values listed for our ASTM 36-inch structural steel. Now we need to go in and work on our geometric values. Let's draw the cross section out with as much information as we can. And I like to label everything because we have to refer back to this often, and I don't want to grab the wrong term by mistake. And from here we can calculate the effective area, which would be pi r squared minus r squared, 4.52 inches squared. We could calculate the polar area moment of inertia, which will be 1/2 pi r to the fourth minus r to the fourth. And if we plug in our 3 inches and our 2.75, we'll get 37.4 inches to the fourth. Interestingly, we can check that with our equation for thin-walled pipes, where we use R average 2.875, and we'll get 37.33. So it's close, and it's your call whether you want to use the other value or not. The I for this will be 1/2 of J, and that'll work out to be 18.7 inches to the fourth. And we need the Q as well. We might as well compute everything. Now the Q will be the largest along the neutral axis, which will be the axis right here if we cut this tube in half. And we can do that as composites, so it would be A y bar of the larger segment minus the A y bar of the little inner segment. And from there we'll get 1/2 pi r squared. And recall the y bar for a half of a disk is 4r on 3 pi minus 1/2 pi little r squared for little r on 3 pi. We can factor out these common terms of 4 on 3 pi, and we'll get 1/2 pi times 4 over 3 pi times r cubed minus r cubed. The pi's will go, the 4 will turn into a 2, and we find a nice shortcut for calculating the Q of hollow round pipes as 2/3 of r cubed minus r cubed. If we plug in our appropriate values for r, we get 4.135 inches cubed. And that's a formula worth keeping. And our last data point will be T. If we are making a cut here when we're doing our VQ on IT, and notice we have to cut it in 2 places here, 1/4 plus 1/4, or 1/2 of an inch in total cut. We could add C, which is the distance to the outermost fiber, and that would be 3 inches. So all of our geometry is done. Next we need to address the loading effects at the base of the column down here due to these inputs of load above. And notice that we've got 4 areas to address. An element at A at the front, B at the side, C at the back, and D on the other side. And we'll find that if we look at A and B, we'll be able to infer what's going on at C and D. So our first step is to take the loads up here and figure out what their effect is down here on this cross section. So draw a rough cross section of the base and identify the location of the points A, B, C, and D just to keep track of our references. And now we'll look up at the loads here, and let's do the compressive loads. We have a total load P pushing down on this element of WS, the weight of the sign, plus WP, the weight of the pole. Both of those are in the negative Y direction. So that'll be 2 kips plus 1 kip will be 3 kips. And we'll show that as a vector into the board as opposed to a vector which is out. So down here, put an X on that, and that'll be a P into the board. And we note that that's going to be in compression at that point for that element. Next, let's take FW. Recall the process for moving vectors. If you have a vector, you move it down to the new point and bring any moment it generated with it. So for the wind force, the base of the column will feel that. It'll be a half of a kip. That'll be the shear. It's trying to shear this off of its base. Now we also need to bring any torque or moment that brought with it. So we can see here that that generates a torque around the pole. So let's get the torque around the pole due to F, and it'll be Fw times the distance to it. Fw is 1/2 of a kip, and it's 8 feet, so that'll be 48 inches to the center. So we'll get a torque generated of 24 kip inches, and that'll be in this direction here. Our 1/2 of a kip load from the wind is also generating a torque in this direction as well, which we would call a bending moment, and that would be the force times the distance, and this is 12 feet, 1 foot to the center. That would be 11 feet up to that point. So we have a moment due to F, so that would be force times distance, and we have a 1/2 of a kip times 132 inches, again watching out for our units. And that'll give us 66 kip inches of a moment generated. And notice that it's in the negative X direction, if you want to call it that. I tend to show moments with double-headed arrows to keep track of them. And remember, its direction is given by right-hand rule. So if we're bending this, the right-hand rule tells us that it's in that direction. So to move the force down to here, we have to first move the force itself. We inherit it directly, but then bring any moments it generates. And it generated a torque about the pole, and it also generated a bending moment about the base due to that height above there. Now we're almost there. This weight of the sine, so that's going to generate a moment of 2 kips times 4 feet. So the moment due to the sine's weight, and it pays to notate all of these, we have the weight of the sine times the distance, which is 48 inches, 96 kip inches, and that will act. You take a second and look at it. Where do you think it will act? It'll act in the C direction back here. By the right-hand rule is torquing it like that. Your thumb would point in that direction. So we'd show down here double-headed arrow as a moment, and it's in this direction, and it's 96 kip inches. We need to invent some new unit here, like a kin or something like that, which would be a kip inch. Although I guess people might think of it as a kilo inch too, or they won't know what the heck we're actually talking about. Sorry, I'm just rambling. Our next step is to take those loads and determine all of the stresses that could be acting at the base of this column. And I like to calculate all the maximums of these first, and then use those values to determine which ones are acting at the different elements of A, B, C, and D. So let's start there. Our stress normal will be P over A, and P is 3 kips, and we have the A of 4.52, and we'll get 0.664 KSI from that. We can compute the bending stress, and there's 2 of them. So we'll do the bending stress due to the weight of the sine. That'll be MSC on I, and it'll be 96 kip inches times 3 inches divided by the I of 18.7. And we'll get 15.4 KSI from that. The other bending stress will be due to the force of the wind, so that'll be MFC on I. And C and I are the same here since it's a round column. And MF is 66 times 3 on 18.7. We get 10.6 KSI from that. And now the shear stresses, we can do tau due to the shearing force V, we know is VQ on IT. And our V was 1/2 of a kip. Q is 4.135. I is 18.7. And T we know is 1/2 of an inch. From that we get 0.221 KSI, a very small shear. And lastly would be tau due to the torque acting, which is TC on J. And again, here's where it's nice to have all of your numbers listed on the side. We can just pick them off the list. So the torque is 24 kip-inch times 3 on J, which is 37.4. And we get 1.93 KSI for the torque-based shear stress. So with that, we have 3 normal stresses and 2 shearing stresses that we now need to address with how they react with these elements down here. Let's start with element A. And I like to put the units on it, KSI, and I'll put a reminder that it's on the front. And one by one we'll go through and figure out which of these types of stresses are acting on that element and in which direction. So the normal stress, that acts everywhere. All of the elements are going to be crushed uniformly by that all the way around. So that one will be on all of them. 4 KSIs from that. And this bending stress due to the S, that's over here. So if we look over here at our loading diagram, that moment by the right-hand rule will be torquing it this way. It's going to be compressing B. It'll put D in tension, and both A and C are on that neutral axis. So a bending stress on a neutral axis is 0, so it doesn't affect A. But if we look at the bending stress due to force F down here, that's acting this way, and by the right-hand rule it's torquing it like that. That'll put C into compression and A into tension. So we'll have a tension stress here of 10.6 from that. And it's important to get used to looking at the 2 different neutral axes, depending on which element we're looking at. So A is on a neutral axis, B is on a different neutral axis, and that'll switch which of these are at play at any given time. So please try to become comfortable with the idea of working with 2 neutral axes. That takes care of the normal stresses. Let's look at the shearing stresses. Now, I'll start with the one based on torque. The whole tower is being torqued by this torque T, which means all of the elements are going to have that shear force acting on them. And if you looked at element B, let's say, you can see that that torque is going to cause it to elongate in that direction. It'll be the same for A, and that's a hint as to which direction the shear stress acts. On our element, it's going to act in this direction, and it's trying to torque or shear this element like that. And that'll be 1.93, and we'll see that on all of them. And the shear stress due to the V force. Now the V force is acting in this direction, and recall that if you're on the neutral axis for V, which would be B, that's going to be a maximum tau. And if you're at the outermost fibers, that's going to be 0. So element A is at the outermost fibers for the neutral axis associated with tau V. So that's 0. It won't affect that element. So with that, we have all of the stress. And I like to put the resultant values on the other end of the element. So here, acting down, we have 9.94 KSIs. And on the right side here, I can show the other complementary property of shear of 1.93, and those are the net results. And that's just notation to try to keep track of all these values. Now let's look at B on the side. For element B, it's being compressed by that 0.664. Every element feels that. Now for B, these bending moments, if we look here at B on the loading diagram, the moment due to S is pushing B into compression and D into tension, so that is going to be a max. And the moment due to F, B is on that neutral axis, so there won't be any stress due to MF, but there'll be the maximum value of compressive stress due to MS. So we'll have a downward acting 15.4 KSIs from that. And from a shear stress, from the shear stress point of view, all of them have the 1.93. They're all being stressed by that torque that's acting in the system. And now let's look at tau V. V is in this direction. B is the neutral axis for that. The horizontal shear stress is always a maximum on the neutral axis, and it's trying to push the element backwards like that. So on this element, that will show up a stress in this direction of 0.221. So they both are additive. And our resultant values will be 16.1 in compression here, and a shear upward here of 2.15 KSIs, and that's our net values associated with that. And so far, those are the peaks that we've seen, so I'd be concerned about element B. Let's next take a look at element D, if I can fit it into here. This will be the left side in KSIs. And it would help here to identify which direction is the front. So for D, that's the front of the beam. And for B, that's the front looking direction. So we're on the other side here staring at element D, and that's the front according to that element. And it's important to be clear about that so we can get these directions correct. Now, these two elements share a neutral axis, which means these values will mostly be the same, just some of them will switch direction. We have the same 0.664 acting down. All of those elements are in compression due to that. But this 15.4 over here, we're torquing this thing, and that's putting this element into compression, while element D on the other side has to be in tension, therefore. So that will give us 15.4 up. Regarding the shear stresses, we still have our 1.93 in that direction. However, on the element due to V, we're going to be pushing it backwards towards the rear of the pole, so that little 0.221 is going to turn over and act in the other direction. And the result of these will be a tension value here of 14.7 and a shear stress, I can show it over here on this face, of 1.7. Remember our complementary property of shear, it acts like that on all the faces, so we can show it on any face that we want. Now let's take a look at element C. I think I can squeeze it in over here. And again, these share a neutral axis, so that's going to make it easy to compare those two. All the elements have the 0.664. This 10.6 will flip over and act down on this one. And if we look over here, we can see that it's this bending moment that's doing that. It's bending this way, and it was in tension on A, and it'll put C into compression in the back. So that's what that 10.6 is showing. And our shear stresses, every one of them has the 1.93, and it's in the same direction on every one of them because of the way the torque acts to twist them all in that same pattern. And the horizontal shear will be 0 because we're on the outermost fiber for that element, and that's our state of stress. So we have then 1.9 KSIs for that, and a compressive stress of 11.26 KSI. So with that, we're able to analyze all four of these elements, choosing A and B to start with, and then recognizing that elements that share a neutral axis are a little easier to work with side by side. And with that, I'm concerned about B. It appears that B has the largest compressive stress. So let's take B as our maximum condition, and we'll do more circle analysis on it to see what the peak stress will be. To draw more circle, let me just identify this as X and this is Y. And it'll just be true for this element to keep track of it. It won't be representative of the system itself. So stress X is 0. Stress Y is negative 16.1. Stress average then will be the average of these two numbers, which will be negative 8.05. And tau Y, let's use, will be 2.15, and on the y face it's clockwise, and there's our data. So now we can draw a more circle where the tau clockwise and tau counterclockwise are on that axis, and the x-axis is stress x and stress y, and we have negative 16.1 here, and half of that is negative 8.05. So our y end of our rotator is someplace on this line, and tau y will pin that for us. We have a tau y of 2.15. It's fairly low. So where these two cross will be the end of our rotator. So that'll be y. And if we run a straight line through here, we'll see that the other end of the rotator hits the y-axis. Stress x is 0. It's on that specific axis. And then if we look inside of here, here's our little triangle that we want. So it has a height of 2.15, the shear stress value, and a base of 8.05, so we can calculate R. R will be the square root of 8.05 squared plus 2.15 squared, which will be 8.33. And stress max then will occur when we rotate this down to here, and that'll be stress average plus R, which will give us 16.4 KSI as our peak value. So there's our maximum condition to design for. And while we're at it, we could also find this 2 theta here. 2 theta P is tan to the minus 1 of the opposite 2.15 over the adjacent 8.05. So that works out to be 15 degrees. So theta P, not that we really need it, is 7.5 degrees. So a small rotation of B, and the Y face would see a compressive stress of 16.4. And interestingly, tau would be 0 at this condition, and that would be 7.5 degrees of rotation. It's really just this number that we need. Now we can also find tau max, and that'll occur if we rotate this up the other way, and that'll read off tau max for us, and see that it's equal to R. So that'll be R, which will be 8.33 KSIs. With that, we can now complete our safety factor computation. Our safety factor for compressive stress will be the compressive yield of the steel divided by the maximum that we experienced in our beam, and that's 36 KSI over our 16.4, which gives a safety factor of 2.2 based on compressive stress. And we have a safety factor based on the shearing stress. That'll be tau yield over tau max. The yield stress for the steel is 21 KSI, and our peak value for tau is 8.33, which is 2.5 safety factor there. Now we picked the lowest of those two, which is 2.2, so our final answer is a safety factor of 2.2. And it might seem like a lot of work, and that's because it is. And that's why engineers get paid so much money, because it's a lot of details to keep track of, and it's a lot of individual terms that you need to know how to calculate and what they mean, and how to manipulate them, and to understand when things are maxing and minning. And that just takes practice and time and a lot of attention to detail. So thanks for watching. That one was a doozy.